computer.
Yep, there it goes.
Right. Okay. So just to rehash for those of you who are just chiming in now, who are watching this video, I was just saying that you should be able to come up with Darcy's law little q and Darcy's law big Q, and that the idea that hydraulic head is what determines the direction of groundwater flow is just the most fundamental component of water flow. And you guys remember the two components of hydraulic head? What are those?
Elevation head and pressure head.
Elevation head and pressure head, that's it. And so there was an exercise which I thought we might kind of, even though I was going to post the key, but did you guys do this homework? I signed that. It was on Moodle. It was part 2 of that, of one of the other exercises. I think it had this on the first page. And then this was the second page. Did you guys do that? I wanted to give it to you because it seems it's a little tricky for people to wrap their brain around at first. Have you seen this? Give me the thumbs up if you've seen this before. Okay. So if you're doing the homeworks, this was page 2 of one of the homeworks that I posted. And I wanted to just drive home, because hydraulic head is so important. I wanted to kind of go over this together because it really, I think, illustrates a couple of points. So let's see if we can do this here. So each one of these dashed lines on there is a contour line. Remember what contour lines are from topographic maps, right? They connect points of equal elevation. The dashed lines here are connecting points not of equal elevation, obviously, but points of equal hydraulic head. Okay, so it's like a topographic map, but instead of elevation, you're just mapping out hydraulic head. So far, so good. Can you tell that my mouth is moving if I don't? I'm actually talking right now, and yet you can't. I'm looking at my picture. I can't actually see my mouth moving. It's pretty cool. You'd have no idea I was talking if you're just looking at this video. Could you?
Well, the box highlights whoever's talking, so.
Yeah, but you can't tell from, what if I roll her down like this? Can you tell now? You still can't tell. That's pretty good. Anyway, so water will always flow from high hydraulic head to low hydraulic head, right? If you think of a topographic map, I'm going to draw a topographic map here. So this is 100, 90, 80. So just sketch this topographic map, right? If you were to drop a ball somewhere on this map, how would you know where the ball would roll based on these contours?
Assuming there are contours of elevation, it would roll perpendicularly to the lines going higher to lower.
Right. So it's going to go from high elevation to low elevation. That's the way a ball is going to roll, right? Obviously downhill. But it's also going to roll perpendicular to the contour lines. And you think about that, if you have a hill like this and you drop a ball,
so it's going to like roll almost up back towards the other corner?
Yeah, so I mean if you have a plane that looks like this and you drop a ball here, it's going to roll straight down. It's not going to roll kind of sideways, because then it would essentially be defying gravity, right? It would be moving horizontally as well as vertically. It wants to go take the straightest, most direct shot downhill. So if you drop a ball here at the X, right? Look at that and plot out exactly how that ball is gonna roll. Just think of it in your mind, and then I'll draw it. You got it? Okay, here goes. I'm gonna take it away. It's gonna go like that, more or less. So that wherever the ball rolls, it should create a 90-degree angle with the contour line. That's what I tried to do there. You got it? Okay. So the same would be the case with this. right? When a molecule of water is flowing, just take any point on this map and imagine that you have a little molecule of water somewhere and it's moving. It's going to move from higher hydraulic head to lower hydraulic head, and it's always going to move perpendicular to those what are called equipotential lines or contour lines of hydraulic head. Does that make sense? So if I was to put a dot right here, see the X there, right there? Where would a molecule of water go if you gave it enough time?
The pool of water.
Say that again, Tommy?
The pool of water.
Yeah, go up to the lake. So I'll draw it out here. But we'd expect it to go kind of like that. Right? It's going from high hydraulic head to low hydraulic head. So the next question, though, is how do you know what the hydraulic head is for each one of those? They're not labeled, right? It doesn't, like this one, on this topographic map, I actually wrote down the numbers corresponding to the elevations. But on this thing, there aren't any contour lines there, right? I mean, excuse me, any numbers on the contour lines. So this is sort of what I wanted to get into. How do you know what the how do you know what the hydraulic head is for any one of those contour lines? How could you figure it out? Do you guys have this in front of you? Did you print it out? It would be easier if you could pull out the one that you printed rather than me holding it up like this. But if you don't have it, that's okay. You guys all get the question? What are we trying to do? We're trying to assign a number. Hydraulic head is a number, right? It's a height. Agreed? Mm-hmm. So we need a height for the hydraulic head that corresponds to every point along each one of those lines. So everywhere along each line is going to have the same hydraulic head. So how do we solve that?
With elevation.
Okay, but the elevation at any point along these curved lines is different.
It's the elevation and pressure head that makes up the hydraulic head.
Okay,
and
that's
so the
good.
Pressure, yeah, so the pressure gets, they are inversely related, so the pressure would get higher the deeper you go. So
okay, yeah. True. Mm-hmm. So how do you know then exactly? You know that pressure head plus elevation head equals total head. And we wanted to know the total head value that corresponds to each one of those lines. So we've got essentially two unknowns, one equation, right? We don't know anything. So how do we solve for that?
You find a point on the line where one of the two is 0.
That's it. So at what point on what line is one of those variables 0?
When the pressure head is 0, it's at the same height as the water level, water table.
Yeah, that's it. So what I'm going to do is try and draw that in here. Imagine that. So that orange thing that I just drew is a well. All right, so you guys all clear what we're looking at here? We've got the land surface, that's the top line. And then we've got the water table right underneath it, right? So from the water table up is the unsaturated zone. That's where some of the pores are filled with air. And from the water table down, it's the saturated zone. That's like the aquifer. All of the pores are filled with water. So if you were to drill a well that went from here and went through the soil, went through the unsaturated zone, here's the water table. And the well The well comes down and stops right at the water table. Does everybody picture that? How high up inside the well is the water rising?
I mean, none.
0. Right? So if we remember what the equation for a hydraulic head is equal to the elevation head plus the pressure head, right? Total hydraulic head is equal to elevation head plus pressure head. You think of a well, that's how the two components of hydraulic head are sorted out, right? From sea level up to the bottom of the well, that's the elevation head. And from the bottom of the well up to wherever the water is in the well, that's the pressure head. Agreed? So look at this equation here. The total head is equal to the elevation head plus the pressure head. If we drill a well so that it just comes down and touches the top of the water table, then the water is not rising up inside the well at all. Agreed? So what is the pressure head?
0.
0. So the pressure head is 0. So if the total head equals the elevation head plus the pressure head, but the pressure head is 0, then what does the total head equal?
It equals the elevation head then.
It equals the elevation head, right? So what is the elevation of the bottom of the well here? Right where I drew it.
$60.
Sure, 60. So what is the elevation, excuse me, what is the hydraulic head of every point along that dashed line?
60.
60. So if you were to drill a well here and it goes all the way down until it touches that dashed line, right? How high would the water rise inside the well? Let me draw it. I drill a well here. It looks like that. How high will the water rise in the well?
It wouldn't rise?
No, it will.
It'd rise
No.
about 40.
To the water table?
Yeah.
Oh, I see.
It would rise up until the water in the well is at what elevation?
60?
60, right? That is the hydraulic head for every point along that line. So the water would rise up to the same height here, same height here as it is right there. How do we know that the water will always rise to the same level? Because we know that both wells are touching that hydraulic head contour line. The hydraulic head is the same along every point along that line, right? So no matter where you drill a well, if the bottom of the well touches that dashed line, the water will rise up to 60 feet. That makes sense? Hopefully. So what I want you to do, if it sounds like a lot of you haven't done that, is go back and finish the rest of this exercise. Okay, as not now, but as homework for tonight. You'll have another exercise or two, but that's an important way to do. The other ones, I'll post I'll post the key to, and those are more straightforward. But that's the one that you have to sort of think through a little bit. Okay. Now later on in the class next week, we're going to start looking at once we kind of understand a little bit more about the way groundwater moves, we'll take a really big step back and we'll look at regional groundwater systems. So these are really, really important. Like in the Midwest, there are these regional groundwater systems where the bedrock kind of dips from, say, Minnesota is where the limestones and stuff are cropping out at the surface, and then they dip south. So by the time they get under Mount Vernon, they're maybe 800 or 900 feet below the land surface, right? And the rain and snow that fall up in Minnesota soak into the ground and they get into those rocks, and then they just kind of gradually glide down over thousands and thousands of years until they're underneath Mount Vernon. So that's kind of a big regional groundwater system. And so we're going to start looking at that. Well, one of the ways that we describe regional groundwater systems is by drawing flow lines, which is like where the water would go. And how do you know how to draw a regional flow line? Well, you need those equipotential lines. You need these contour lines of hydraulic head. So you'll start seeing those on these big regional maps, and you just think of them like contour lines on a topographic map, right? Wherever it's higher, that's where water's coming from, and wherever it's lower, that's where water's flowing to. Okay. All right. Anyway, so let's get started on this exercise that we're going to do today. You guys all watched the exercise on subsidence and effective stress and fluid pressure? Yeah. And you read the USGS thing on subsidence? Wasn't that crazy? Does that, I don't know, that kind of stuff just blows my mind. The photograph of the guy from the San Joaquin Valley standing next to that telephone pole or power line or whatever it was with the dates on it. I mean, that's pretty incredible, right? I mean, we like to think that humans are kind of passive when it comes to Earth's surface. You know, we can take bulldozers and we can move stuff around, but I mean, you're talking about taking entire huge parts of the Earth's surface and just dropping it like you just pushed a button in an elevator, you know, and it went down 30 feet. It's pretty remarkable. And it obviously has really big consequences for people living there, right? If you drop 30 feet, you are now much more prone to flood than you were 100 years ago, things like that. Anyway, okay. So we talked about the fact that there's this effective stress, this total stress, which is the sort of the weight pushing down, right? And it's balanced by two things pushing back up. What are the two things that push up that hold the rocks in place?
Effective pressure and fluidic.
Effective stress and fluid pressure. So the fluid pressure, you guys all know what fluid pressure is. Like the more water you put into a water balloon, the more pressure it's under, right? And the effective stress is basically how hard each little sand grain is pushing against its neighbor, right? So in an unconfined aquifer, does the fluid pressure carry any of the weight of the overlying material? Why not, Tiff?
Because just there's nothing like in a confined aquifer, there's nothing enclosing it, holding anything up like in a confined aquifer. So in an unconfined aquifer, it's the fluid pressure isn't there because it's not holding anything up. Yeah,
if you were to increase the fluid pressure in an unconfined aquifer, what would happen to the water?
It'd rise.
Yeah, it would just squirt up, right? It would just rise up and fill cracks and pores higher up. The reason that fluid pressure is important in confined aquifers is because the water can't get out of there, right? It's not free to just squirt out when it's under more pressure. And so as the pressure builds, it's able to carry more and more of the overlying weight. Make sense? But in an unconfined aquifer, if you were to increase the pressure, the water would just squirt out of there. It would just leave. So it's not going to do any lifting. Okay? All right. Now, as I mentioned in the lecture, right, the total stress, the force pushing down, is balanced by these two things pushing up. And if one of the ones pushing up changes, or if the thing pushing down changes, there has to be a response from the other side, right? If you keep the total stress pushing down the same, and you increase the fluid pressure, then what has to happen to the effective stress? It's got to go down, right? If this is balanced by these two things, this one goes up, then this one's got to go down by the same amount. Agreed? Okay. All right, so I'm going to ask you to go to Moodle. And on the Moodle page, there is a, where is it? Where is it? Did I not post it? Maybe I didn't post it yet. Okay, hold on. I'll post it now. Here it is. I didn't post it. Where the hell did it go? There it is. Okay, so under exercises, there is now an exercise called blowout exercise. It's on the bottom, I think.
Yep.
So what I want you to do is I'll divide you up into groups again. And I want you to read through this carefully before you get started. Make sure you understand it, and then try to and then try to solve it. So there are these terms in there which I think I've defined appropriately, but one is called weight density, which remember that, let me ask you this question. How do you calculate the total stress pushing down on something? We did this in the lecture video.
Is it effective stress plus fluid pressure?
That's true, but if you want to calculate total stress just independent of fluid pressure and effective stress, how can you calculate it?
It's weight and gravity. It's been math.
Okay. So it's gravity times what?
The
Weight
height
and
of
density.
overlaying material.
It's gravity times the height of the material times the density of the material. Right. Okay. So to make things easier, what sometimes people do is since gravity is a constant, they'll multiply gravity times the density of something. Like the density of water is 1,000 kilograms per cubic meter, and gravity is 9.8, meters per second squared. So they'll just multiply those together, and you get 9,800 newtons per meter, whatever it is. And when you multiply gravity times density, you get this term called weight density. And that's in the problem, I think, here. I think I left it in. It doesn't matter, as long as you know that that's what that is. Okay, so anyway, I'm going to divide you up into groups, and I'll pop around and make sure you guys are off on the right track. But again, the first thing you need to do is just on your own, spend a full minute reading through this and make sure you understand it. Okay? All right, good luck. I'll invite you to breakout rooms right now. Let's see, how many people are there? 16 participants. Yeah, that's good. Okay, here we go. You guys see the invites?
Not yet.
Yep, there they are.
Okay, cool. All right, hop on in. I'll catch up. Hey, yep.
Hello.
Just ignore me unless you need me.
Just reading through it.
Yep, good.
What's the gravel that it's referring to in the second paragraph?
Oh, I thought I took all that out. Sorry. It's just the sand. It's supposed to be the sand.
Okay. All right.
Sorry.
All right. Has everyone read through it?
Mhm.
All right. So, first thing we're going to calculate is the total and effective stresses and fluid pressures at the top of the
5, 8, 5, 7, 5, 7, 7-ish. So, oh, hey there.
Hi.
I have a question. When you say gravel,
Yeah, it's a typo. It's meant to be sand.
okay, just checking.
Sorry.
Yeah. Okay. So when you dig the trench 10 meters deep, you're changing the total pressure because now you're only accounting for 30 meters worth of 20,000 weight density, correct?
You're
So the
changing
total pressure goes down,
total stress. Yeah.
total stress. But the fluid pressure stays the same because the pressure head is still 33 meters.
Right.
So the effective stress drops by
Whatever.
to account. Yeah.
Yeah.
So
That's
if
it.
the trench is dewatered, you're trying to consider if the new effective stress is lower than the total or the total stress. And if they are, if the effective stress is lower, it will be blown out.
Well, work through it in stages.
Is that how this works?
Yeah, you're on the right track. Work through it in stages, and then when you get to that final part, that's where you have to deal with the blowout. So have you already
Okay.
calculated the effective stress and fluid pressure and everything?
Yeah, I think so.
Okay.
223-ish. Yeah. So I have a new effective stress after the trench, and I have a total stress after the trench. So now, ignoring the fluid pressure, we compare those two.
Okay, so the first thing you do is you calculate the total stress, effective stress, and pressure at the top of the sand layer, right? Just
Yep.
right out of the gate. And what did you get for those values?
So 800,000 is the total stress. 323,000
Like
for
800,000?
the fluid.
How'd you get 800,000?
20,000 times 40. Is that not right?
20,000 times 40.
The
Where'd you get
depth
that down?
times the weight density.
I think we're calculating what the density would be, or what the pressure would be like under the ditch that they're digging. So that would be 30. 30
Well,
meters.
before the ditch is dug, right? Before the trench is dug, you're asking about what is the
Right.
total stress?
Yeah, so how do you calculate that? That's gravity times density times height, right? Of the
Yeah.
block,
So it gives us the weight density, which is the gravity and density, right?
which is
That's 20.
19,000.
Is what?
19,600?
I see it as 20,000 here.
Oh,
Yeah.
okay.
Am I?
I'm sorry. Yeah, I rounded it off. 20,000 is fine. I had 19,600 on the version I did here. Shoot.
Okay.
Okay, it's not going to matter. That'll be a rounding error. All right, 20,000. And
Yep.
then,
So I multiplied that by 40, the depth, to give us the total stress, right?
holy cow. All right, hold on. Shoot. There we go. Okay. Yes. Okay. All right. So 40 meters is the height of the clay. Yep. Times 20,000. Okay. Yes. I'm with you now.
Okay. So 800,000 there.
Yeah.
And then the fluid pressure is using the pressure head. So 33 times the 9810.
Yep.
I got 323,730.
Okay.
So then you just subtract that from the total stress, and then that gives me an effective stress of about 500. Hold on. Minus 323, 730. 476,270.
Now, are you guys, is everybody in the group on board here? Do you guys all understand what's going on?
Yeah, I got the same values.
Okay.
Okay. And then post trench digging, it's now just 30 times 20,000. So we're at 600,000 for the total stress, but it's the same pressure head. So it's 33 times 9810. We get the same fluid pressure. And then for the effective,
Wait a sec. If you dig a trench and the trench fills with water, the water itself is pushing down, right? It's providing some new total stress. Unless the trench is dewatered, you've got to account for the stress being created by the water in the trench.
okay. So the 3 meters that are underwater.
Right.
Okay.
That's it. You guys are on the right track. I got to bounce around. I'll be back.
Okay.
Hello.
Hello.
How's it going?
Still reading,
Okay.
getting the sense of the problem.
All right. I'll come back. Hello? So, you guys have any questions? Or are you doing okay?
I'm a little confused where to start.
Where to start?
Yeah.
Okay. So what's the equation that you use to calculate total stress?
Total stress is gravity times the density of the material and the height of the material, the
Okay.
overlying material.
So you can calculate the total stress pretty easily, right? By just multiplying those three things together.
Mm-hmm.
And then how do you calculate the fluid pressure?
Is it the fluid density times the gravity times the height of the fluid?
Yeah, what do you use as the height?
Would it be the pressure?
Yeah, that's it. Okay, I'll be back.
Hey, what's total vertical stress?
How do you calculate it?
Yeah. How do you?
Yeah, is that equal to total stress?
Yeah.
Oh, okay.
Okay. Oh, so then didn't we just find? Didn't we? Already
Yeah, well, because now it's, yeah, so. Got it. In the second part, the parameters are changing. They're
That's
gonna,
yeah. That's the only thing that changes is the 10-meter deep instead of 40.
Mhm.
Okay, I'll be back.
A little bit, but I think just because everyone kind of knew what they were doing at that point. Ah,
We have some questions on the trench problems.
Okay.
So we don't know if when they're excavating the trench, are they taking the water out of the entire column or just 3 meters down to kind of match that 10 meters trench excavation?
So let's see. So they dig a 10-meter deep trench.
Yep.
And it fills with water all the way to the land surface, right?
Okay.
So that's the first calculation. And then the next calculation is if the trench is dewatered. So the next question then is what happens if they pump all the water out of the trench and keep all the water out of the trench?
Right.
Oh, so they are keeping it out. They're not just pumping it out once. Okay.
They're keeping it out. So when you have water in the trench, the water is supplying some of the downward total
Yeah.
stress, right? But when you pump the water out, the trench doesn't weigh anything. So that's just 0.
So there's 30 meters of water sitting on top of the sand aquifer
Sure.
in addition to the clay that it's in.
Yeah, 33.
But wouldn't it be 30 because the trench is 10 meters deep?
So you have to, this is a little bit tricky. You have to think of the clay and the sand as basically 2 separate aquifers that aren't talking to each other. So the sand is a confined aquifer. It's totally filled with water.
Right.
And when you puncture it with a well, it's under enough pressure that the water rises up 33 meters above the top of the sand. The clay, which is sitting on top, is like its own aquifer, and it's completely saturated with water.
Mm-hmm.
So that as soon as you put a shovel into the clay and throw it away, that hole fills up with water.
Okay, so they're separate. Okay.
Yeah.
So we have to like tease out the clay and the water kind of section together so that we can find out just what the clay weighs, what it's pushing down, and then we subtract like the water from that.
Well, right. So you can just do it that way, or the easier way probably would just be to think of it as two columns stacked on top of each other, right? One is 10 meters deep and it's just water, and one is 30 meters deep and it's clay plus water. And when you add those together, what's the total stress from both of those together? That make sense?
I think so.
Yeah. That's
okay. All right, work on it. I'll be back.
So we're not doing any math for the sand then, right?
Nope, I came back to the wrong one.
Oh, hello.
How's it going?
We're kind of confused on the units. I'm not sure if I even did this correctly. I think I'm stupid. I'm like really confused right now.
Okay, let's talk about it.
I assumed in the exercise that 40 meters was the height of overlying material. I don't know if that's correct or not. For the total stress, it's that times the density and the gravity. And in the exercise, I assume that's what they gave us, the total weight density. It says defined as gravity times density.
Mm-hmm.
And it gave us like 20,000 newtons per, I think it's meters cubed. I'm not sure if that's the correct unit. And I thought we had to multiply those, but I'm not sure, Ron. I'm really lost, honestly. Like.
Okay. Yeah. So you have, if you look at that graph down there, the figure's a little bit confusing. But the way you have to think about this is as 2 separate aquifers that don't talk to each other, one stacked on top of the other. So you have the sand aquifer down below, which has enough water pressure that when the well is drilled through the clay down and just touches the top of the sand, the water pressure causes the water to rise up 33 meters above the top of the sand. Okay? The other part, does that make sense so far?
Yeah.
Okay. The other part of it is this clay layer, which is sitting on top of the sand, and it's clay and it's completely saturated with water so that the water goes all the way up to the land surface. So if you stick a shovel into the clay and pull it out, water would rise up and fill that hole all the way up to the land surface, okay? So what we want to do is we want to calculate, first off, what is the total stress pushing down on the top of the sand? And so it's, as you guys have said, the way you calculate that total stress is it's gravity times the height of the clay times the density of the clay, or the clay plus water. And you're given the density times the gravity of the clay, which is equal to 20,000 newtons per meter cubed. You see that?
Yeah.
Okay. And you're given the height of the clay as 40 meters.
Yes.
So if you multiply 40 times 20,000, you get 800,000. That's the total stress pushing down on the top of the sand layer.
Okay, I got that.
Okay. The fluid pressure is calculated as the density of water times gravity times the pressure head, which is how high the water rises in the well. And you're given that the weight density of water, which is gravity times the density of water, is 9,810 newtons per meter cubed. So you multiply that by 33 and you get the fluid pressure.
Mhm.
So then to figure, go ahead.
All right, what is the units for both of those? Is it the Newton meters cubed or?
Yeah.
It is? Okay.
Oh, wait, sorry. No. It would be newtons per meter squared when you multiply it by the distance.
For the 800,000 and the 300?
Yeah. Newtons per meter squared, right?
Okay.
And you've heard of that sort of thing, right, before, like pounds per square inch. You ever heard of somebody talking about how much pressure there is, pounds per square inch?
Yeah.
Anyway, that's where that comes from. Okay. So you know that the total stress pushing down, which is 800,000, has to be perfectly balanced by the two things pushing up, which is fluid pressure and effective stress. And you just calculated the fluid pressure. So you know the force going down, you know half the force going up. So how do you calculate effective stress?
Subtract.
You subtract, right? So you get it. So then, I mean, if you can do that, then the rest of this is really easy. So now that the next thing is, they say, what happens if you dig a trench from the land surface down 10 meters and that trench fills all the way up with water? What is the new total stress at the top of the sand directly below the trench? How do you calculate that? Justina, how do you calculate that?
Would you, so I'm not sure exactly. Would you subtract? I'm honestly lost.
Okay. So you have two different little, think of it as like two different rectangles. Like this. Just writing this out here. You see that?
Yes.
So wait. The thing that I'm calling A, that was what you did a minute ago, right?
Yes.
You took the height of this column of clay plus water, you multiplied it times the density of this clay plus water, and you multiplied it times gravity, and you got 800,000.
Mm-hmm.
Here we have only, what is this, 30 meters now of clay plus water? We dug a 10-meter trench. Is that right? Yeah. Right? This thing is 40 meters high. We just dug a 10-meter trench, and that's filled with water. So that means this is only 30 meters high now. Do you picture that or no? Justina?
Kind of. I'm sorry. I'm just trying to get used to like visualizing.
So this is the land surface. And we dug a trench. You know what a trench is, right? Like a hole,
Yes.
right? So we dug a trench down to here, and it's 10 meters deep. And this whole thing from the land surface down to the top of the sand is 40 meters. So that means this has got to be 30 meters.
Yes.
So you could calculate the total stress, just like you did over here. You could calculate it for this portion, right? Instead of being 40 meters high, though, it's 30 meters high.
Oh, okay.
But there's also total stress coming from the weight of the water in here, right?
Right.
How would you calculate the total stress coming from this trench filled with water?
Would it be? So we have 10 meters and we would multiply that.
10 meters times what? How do you calculate total stress? What's the equation?
The height of the overlaying material times the density and the gravity.
Okay. So what is the total stress coming from this water right here? How'd you calculate it? What's the equation? You just said it.
Well, it's the height, right? And the density and the gravity, like all of those.
Okay. So what is the height?
10, right there.
What, you know what gravity is? And what's the density? Or what's the weight density? Gravity times density of the water.
Well, isn't it given to us?
It is. And what's the number?
20,000.
Nope.
Oh, wait, sorry. 9,810.
Yeah.
Okay.
So you can calculate the total stress coming just from the water, and you can calculate the total stress coming from the clay plus the water, and you get a brand new number for total stress pushing down on this top of the clay layer, or top of the sand layer. Right?
Right.
And when you do that, will the fluid pressure change? The fluid pressure pushing up, is that going to change? The answer is no. It's not going to change the fluid pressure. But if you're pushing down less and the fluid pressure is the same, what has to change? Who's that over there? Riley? What has to change, Riley?
Is it just the porosity of the
No,
sand? Or the, oh,
I mean, it's related to the porosity, but
the density of the material
sort
in
of.
between.
But what's the term that we've been using?
Oh, the weight density?
No.
No.
Total stress is equal to fluid pressure plus
Effective stress.
effective stress. So the effective stress has to go down, right?
Yeah.
Okay. There you go. So keep working on it. I'll be back.
Minus 20,000 X.
Tommy, can you hear me?
Yes.
I was just using that Who quote again. I can't.
Yeah, I know. I went and listened to it. It was good.
All right, how's it going?
Pretty good. I think we just worked out the last one, the watered filled trench. Chloe, do you want to walk us through it here since you got the right answer there?
Yeah, did you guys both figure out the equation we're using? I think.
Yeah, but I was using that equation and I'm still getting a positive or a number that doesn't make sense yet.
Negative?
So,
I haven't completely worked through it yet, but I'm getting there.
yeah, I'm still getting 46.739 is the depth of the trench, but
we were good up until we started doing algebra, right?
Yeah.
So did you get negative 476,270 is equal?
That would be this minus 800,000.
Right.
So you set X equals to the depth of the trench and 40 minus X is the clay layer?
Yes. Yep.
Yeah.
Okay.
Minus 98.
Yeah, I didn't. I had solved this using different numbers, so I don't have the numbers here. I'll have to post it in a minute. But as long as you get to that point, you're fine.
Mhm.
Just a matter of, like you say, solving out the breakaway.
Mm-hmm.
Okay, someone's calling me. I gotta go.
Okay.
Right now, I'm gonna.
Wait,
not
how do we
me,
call
like,
you?
No one's like. I'm getting a request to join another breakout room. That's what I mean.
Oh, there's an
know
ask
that
for
was
help
possible.
button. I didn't even
Yeah.
know.
Oh,
I didn't know either until just now. But we're gonna end. I'm gonna end this all in just a second. So you guys
Okay.
finish up, and then we'll talk and wrap up. Okay.
Roger that.
See you in a minute.
Oh.
Yeah. Aha, it did work.
So I had no idea that button existed until
We didn't either.
All right, where are we? What's going on?
We have some numbers figured out. We're wondering if we could maybe check those with you, see if we're on the right track.
Yeah, although the numbers that I calculated were for a problem that had different numbers in it, and so I won't be able to get it exact until I do.
Well, I guess, can we walk you through the steps we did?
Yeah.
Okay. So do you want to do that, Jake, or do you want me to try?
Maybe you could, and I could see if I could follow along with the diagram.
Okay, so to get the total, like overall pressure, we looked at the height, like depth of the clay, which is 40 meters.
Yeah.
We multiplied that times the density, which is the 20,000, to get 800,000.
Yeah.
Then to do the sand, like to figure out the pressure from the sand pushing up for the 33-meter thing, we did 9,810 times 33 to get that like upwards pressure.
For the fluid pressure.
Yeah.
Yeah, for the fluid pressure. Yeah.
Yep. And then to get the, I guess, pressure deficit, you'd like the pressure you'd lose from digging the 10-meter trench. We did, well, I mean, I only wrote it this way. I don't know what the actual equation is because I was just kind of going through the steps in my head, but I had 10 meters was equal to 200,000 because it's a fourth of the total.
Wait. So you calculated the total stress pushing down as 800,000, right?
Yeah.
You calculated the fluid pressure as just south of 330,000, 32,000, something like that, right?
Pushing up.
Pushing up. So the total stress pushing down is balanced by the fluid pressure and the effective stress both pushing up.
Yes.
So if you subtract 330,000 from 800,000,
yeah,
that gives you the effective stress, right?
Yeah, I was just talking about the 10-meter trench. I wasn't talking about effective stress.
Oh, okay. We moved on. I'm sorry.
Yeah,
okay.
I'm just looking at what I had written down. I think I just forgot to write that part down.
Okay, so then for the 10-meter trench, you have 10 meters. Go ahead and explain how you did it.
So in my head, how I thought through it was because you have 40 meters of clay, if you lose 10 meters, you're losing a fourth of that downward pressure.
But you're only losing it completely if it's dewatered.
Yeah, I just had the dewatered part written down.
Okay.
I didn't have the other one written down because I forgot to write it down. It's on my calculator still. But that's what I had for the dewatered part. And I assume you'd have to subtract the weight density of the water part to get the actual one with water still in it.
Wait, so what question are we on here?
So if I did the trench without water, I mean, without water, it's basically just losing a fourth because that's all the material gone.
Right.
If I wanted to have it with the water in it, I have to use the weight density again, right? The 9,810.
Mm-hmm.
And then subtract that or add it?
No, you take the weight density of water and you multiply it times 10 meters because that's the height of the water in the trench.
Yeah.
And you add that to the 3/4 of the original answer.
Yeah, okay. So you would subtract all of it and then you'd add the water back in. Because you'd have 3/4, so you're subtracting the 1/4 of total, and then you'd add the water back.
Sure. Yeah, you could do it that way. Yeah.
And then to get the depth, you can go before it has the bottom. The bottom comes unstable. We had the 800, which is the total, minus the 323,000 to get your 476,000. And then you just divide that by 20,000?
No. So what you want to do is you want to know how deep can you excavate the trench until the fluid pressure. So really what you want to know is when does the
trench collapse?
Effective stress go to zero. So
Oh,
when the effective stress goes to zero, that means that the fluid pressure is equal to the total stress.
Mhm.
So how do you know at what depth that happens? So you have to solve for that algebraically.
So we
Mm.
found out when there's water still in the hole, or when there's no water in the hole, that it equals, you have to dig 23.8 meters down.
So let's see, we have 800,000 has to equal the fluid pressure, which is 9810 times the
33.
wait,
33 is like the quote unquote well that would have been dug.
oh no, so I'm doing this wrong. So it's well, I'll tell you what, there's several people are asking for help here, and we're about to wrap up, but you guys
Okay.
are on the right track. So I'm going to end this. We'll come back together as a group in just a minute, and then we'll sort of work through it together. Okay.
Okay.
All right. See you in a minute.
I misinterpreted.
Aha!
Hi.
Whoa.
You found the secret button. Okay.
We did.
So I'm gonna end everybody's group sessions because you're all getting to the point where you're basically having the same question or questions. So instead of me going around answering them individually, it's much easier to just do this.
Wait, so you already know that's going to be the same
Do you,
question, though?
do you know what our question is going to be, though?
I don't, but I can imagine that since everybody else has similar questions. But all right, go ahead, ask your question.
Would it? Okay.
Yes.
Does it make sense that the water-filled trench can go deeper than the dewatered trench?
Does it make sense that the water fill? Yes, sure.
Okay.
Wait, how? Explain, please.
I will to the group.
Oh, okay.
Oh, okay. So this is a question you've been
It
getting.
was the same question, is what you're saying.
Well, you're on the same track, yeah. Okay, so I'm gonna cancel the breakout room and see you guys back here in a minute.
Okay.
All right.
Professor, I really like that Zoom video you sent.
That was it, Tommy.
Yeah, I recognized.
Isn't that Zoom video amazing?
Yeah, pretty impressive.
It was good, right? I don't know
Yeah.
who the band is or anything, but boy, they did an amazing job. All right, were we missing? Oh, looks like everybody's back. Okay. All right, so I ended this because you guys were all getting kind of to similar points, and I didn't want to keep bouncing around answering the same question over and over again. All right, so let's go over this together. So you needed to figure out the total stress pushing down, and you know how to do that, right? Height, gravity, density. Pretty straightforward. You need to figure out fluid pressure pushing up, which is the density of water times gravity times the fluid pressure, the pressure head in the well. You guys all got that, right? And then you need to figure out the effective stress. And you know that what's pushing down is counteracted by the two things pushing up. So effective stress, total stress minus fluid pressure equals effective stress. Okay, that was pretty straightforward. Everybody has that? Good. Let me see nods or shakes or something. All right. So the next question was, what happens if you dig a trench? Oh, hi, Maya. So if you dig a trench and the trench fills with water, right, then you've changed essentially the weight of the overlying column of material because water weighs less than clay plus water. And we know that because those values are given to you. The weight density, which is gravity times the density of the clay and water, is 20,000 newtons per cubic meter. For water, which would be the trench part, it's only 9,810 newtons per cubic meter. So to figure out the total stress, you calculate them separately, right? You have 10 meters of water and you have 30 meters of clay plus water, and you just add those together. Cool? Now, because you're pushing down less, but the fluid pressure pushing up is the same, the effective stress has to go down. Because you're pushing down, remember, the force pushing down is perfectly balanced by the two forces pushing up. We have reduced the amount pushing down because we created a water-filled trench. The fluid pressure pushing up is still the same. So the effective stress, that grain-to-grain contact, has to be less. And so you should be able to calculate that. Did everybody get that part? And again, I'll post the key. I'm not worried about numbers right now. I'm worried about like concepts. So you guys all got that? Or at least the concept? Okay. Then the next part was, okay, what happens if we stick a hose down in the bottom, a pump down in the bottom of the trench, and we suck all the water out? Now all you have is an empty trench, which doesn't weigh anything, and 30 meters of sand plus water. And so you can calculate the total stress pushing down there. The fluid pressure hasn't stayed the same. The fluid pressure has stayed the same. So the effective stress has gone down even further. Agreed? So then the final question is, okay, and this is the kind of exercise that's somewhat academic, although there actually, believe it or not, are mining applications of these kinds of things. If you want to know how deep you can make the trench until the bottom of the trench literally blows out. And do you guys know what kind of real world material has an effective stress that's essentially zero? That's what a blowout is, when the effective stress is essentially zero, meaning that the weight is pretty much entirely borne by the fluid pressure. What do you call that?
Volcano.
No.
Sinkhole?
No.
Air pressure?
Quicksand.
Okay, it is quicksand.
Right? So when you step on quicksand, the reason you sink in quicksand is because it's essentially floating, right? The water generally is rising up, right? The water's coming up and bearing the weight of the sand. So when you step on it, the sand just moves apart. There's no rigidity there. There's no effective stress to hold the grains in place. And so that just the more you struggle, the more you liquefy the sand and the more you sink. By the way, if you ever get caught in quicksand, you should throw yourself horizontally out on the sand. Don't stay upright, right? You want to distribute your weight over as broad an area as possible, and you'll sink more slowly or whatever. It would be ironic if this someday actually saves your life. And if it does, if you're ever caught in quicksand and you remember that and you throw yourself horizontally on the sand and survive, please look me up and let me know, okay? Because I've never known anyone caught in quicksand. Anyway, so at what depth would you have to dig the trench before the bottom of the trench becomes quicksand, right? Well, quicksand will occur essentially when the effective stress, the force of one grain pushing against another grain, goes to zero. When the effective stress goes to zero, total stress equals fluid pressure plus effective stress, right? Total stress equals effective stress plus fluid pressure, right? When this goes to zero, when effective stress goes to zero, total stress equals fluid pressure, right? That's when you get a blowout. So if you know the fluid pressure, how deep can you dig the trench before the total stress equals the fluid pressure? That's what you had to solve for.
And our fluid pressure is the 323,000?
Yeah.
Okay.
And that doesn't change. So then you just have to figure out how to mathematically figure out how deep you can make those trenches. And the dewatered trench is really easy. The water-filled trench takes another little step, but I'll spell it out for you and post it in a minute. Okay? So that's the basic idea. And this is kind of the opposite in some ways of subsidence, right? But the idea is the same. The idea is that in confined aquifers, the reason we did this whole exercise is just to kind of help you think about this idea, this role that fluid pressure plays in confined aquifers, because when you suck water out of confined aquifers, you're changing the fluid pressure, you're reducing the fluid pressure, right? You guys all focusing? When you suck water out of confined aquifers, you're reducing the fluid pressure, so the effective stress has to go up. And if the effective stress goes up, then that means the rock matrix has to collapse tighter. It's getting squeezed together and it's reducing porosity, and that causes the aquifer to compact. And when it compacts, what happens to the land surface? It
Subword.
subsides.
That word.
I
Subsides.
almost said subducts, and then I'm like, nope, that's
Yeah.
not the right class.
Same.
It subsides, which is what that whole USGS video, that's what we were talking about an hour ago, right? Subsidence. Why does subsidence occur? Because you reduce fluid pressure in a confined aquifer, the effective stress goes up, the aquifer matrix collapses on itself to carry the weight that the fluid used to carry, and the land surface collapses. And obviously, in some cases, this isn't trivial. How much subsidence did they get in the San Joaquin Valley in feet?
Was it like 8 feet?
Like 25 feet.
Yeah.
Oh.
27.
Yeah.
I mean.
Like Mexico City, which was built on an old lake bed, all these clays and sands interspersed with them. When they started pumping the water out of it, Mexico City just sank. And it's happening all over the world because we're constantly mining groundwater or oil, pulling it out, and the aquifer just collapses.
So does that like prevent any aquifers from replenishing in the future?
Yeah. So what did I say about that in the video? I mean, how easily do these aquifers restructure themselves?
I mean, it takes a really, really long time, but I was just wondering if it was like could they, given the same amount of time, replenish themselves, or does the compacting prevent that?
Yeah. So what happens, guys?
You said that it's next to impossible to recover.
Yeah, it's next to
to its
impossible to
original
recover.
state.
So you can fill water in the pores, but the pores are never going to re-expand. Once they're collapsed to a tighter structure, that's sort of the way it is forever. So we won't get it back. Yeah.
So, in theory, if you took water out slow enough, would it just stay the same?
The trick isn't, well, so.
I mean, I know that's kind of unrealistic, but if that was possible.
Yeah, so water's coming into the aquifers all the time and passing through, right? It's always just kind of moving from point A to point B. And what we've done is we've stuck a well down and we've sucked the water out much faster than it can be replenished. So if you were to pull it out at the same rate that it was coming in, right, then you would dramatically minimize the amount of subsidence. But that's not what we've done. Again, I talked about these regional groundwater systems that we'll start looking at next week. And are any of you guys from Western Iowa or Colorado or Kansas or Nebraska, Oklahoma, Northern Texas? There's this huge aquifer that underlies big parts of the Great Plains. And it's named after a town in, I think it's in Nebraska, Ogallala. It's called the Ogallala Aquifer. And it's basically when the Rocky Mountains started going up in the west, all the gravels and sands that were eroding off of this new mountain range started washing out over the Great Plains. And, you know, gravels and things make great aquifers, right? They have lots of pore space. The pores are really big. And so that's buried now down below the land surface by, you know, hundreds of feet or something. And it's like this enormous sponge. And in the early 1900s, with the development of turbine pumps and, you know, electricity running everywhere and everything, they just, out on the Great Plains, they just started sucking the water out. And they built, you know, before that, there were no big irrigation systems on the Great Plains. If any of you guys have ever flown over the west of Western Iowa, and you look down, you see all those all those irrigation circles in the crop fields. You know those things? That's because the water's getting pumped out of the ground and then sprayed out in a rotating arm in a circle, right? Where's that water coming from? It's coming from the ground. And they're pulling it out much faster than it's being replenished. But 100 years ago, they had to wait for the rain. So it was dry land farming. It was like, you know, hit or miss every year. You never knew if you're going to get enough rain to put in a crop. But with the advent of pulling water out of the ground with big, strong pumps, it's completely revolutionized the agriculture there. The problem is we've almost completely depleted that aquifer in about 100 years. It's almost entirely gone, and they're beginning now to start taking very seriously conserving what's left. But of course, that's going to change how you grow crops as well. So anyway, that's something to think about. Okay, good job, you guys. Are there any final questions before I let you go? I'll post this video. I'll post the key from the other day. I'll post the key to today's exercise, and I'll give you your marching orders for tomorrow. But I know that some of you are still sort of wrapping your brain around some of these concepts, and that's of course understandable. That's exactly where you should be. All I can say is keep plugging away. You know, go back over the videos, go over your notes, go over the calculations again. And I keep encouraging you guys, and I really hope you will do this. I'm only getting a small number of requests for you know, one-on-ones, but let me know. I'm just sitting around. So if you want to talk about any of this stuff, reach out to me. Coup de la. All right.
Sounds
All right.
good.
I'll say goodbye, and I'll see you tomorrow at 2, unless I see you sooner. All right. Bye.
Bye.